Nowadays, scanning real physical objects is becoming more and more commonplace. However, high-quality scanning remains a meticulous and tedious task due to physical occlusions, less than ideal material properties, or other uncontrolled operations. Even for an experienced user equipped with a good scanner and a turntable, it can still take hours to obtain a complete surface at high fidelity. We have developed an autoscanner with a PR2 mobile robot. For fast data acquisition, we mount a scanner to his right hand and place a 3D printed resin table in his left hand for holding and turning the object. The scanning process starts with a blind, all-around scanning of the object to obtain an initial point cloud that roughly covers large portions of the object's surface. Our quality-driven, Poisson-guided data analysis can then generate a set of best views for the next acquisition action. Unlike previous scan planning methods, we do not aim to minimize the number of scans needed to cover the object, but rather to ensure the high-quality scanning of the object that is consistent over its surface. The whole scanning process is well planned and iterated automatically until the specified reconstruction requirement has been reached. Given an initial point cloud obtained from a blind, all-around scanning of an object, our core technique is to validate and assess the predicted watertight reconstruction surface. We generate a confidence map for the ISO surface derived from a screened Poisson equation where low values indicate low quality of the estimated ISO surface. We then build an ambient viewing field which suggests a set of next best views with 5 degrees of freedom for covering low confidence areas of the ISO surface. We show that by positioning the scanner at the suggested viewpoints, the surface of the scanned object is progressively captured, recovering all details of the real object. We have also tested and evaluated our algorithm using a virtual scanner on a digital model with unknown shape. Its geometry is rapidly recovered and the details are progressively refined as more and more virtual scans are performed autonomously. The final model captures all features without any topological errors. Blindly scanning a complex object often causes missing parts and losing details. Through globally evaluating the confidence of the attentive watertight ISO surface, we can accurately detect such low-quality areas and apply additional scans. The final reconstruction is faithful to the original object. We compare the performance of our technique to 2 state-of-the-art MVV algorithms, one based on visibility and the other focused on boundaries. On a virtual model, both qualitative surface reconstruction and the quantitative error evaluation demonstrate the superiority of our approach. For a real complex dragon object, our method outperforms these 2 previous approaches, as well as handling close-by surface sheets and recovering sharp features. To better justify our algorithmic decisions, we also compare our technique to 2 simplified approaches, one based on the density and the other analyzing high-frequency scan content. Our method results in a better reconstruction with much fewer scans. Another technique that we compare with is to restrict the view search space onto a sphere. Such simplification may reduce the computation cost, but at the same time limits the precision in scanning complex, self-occluded, or feature-rich objects. We further compared 2 boat models scanned manually by an experienced user and by our PR2 system, respectively. In addition, we use a complex church model to simulate the scanning of outdoor scenes. It shows that our auto-scanning algorithm can be successfully applied to locate next best views in such acquisition scenario. We have also experimented with our algorithm on another robotic platform. This one-arm industry robot allows doing precise moves and so enables us to automatically scan a delicate elephant object at high quality and high fidelity. Note that both geometry and color of an object can be simultaneously captured using our autonomous scanners, facilitating the textured modeling and photorealistic rendering.